Okay, get started a couple minutes early. Um, so exam one, let's go through the problems. And I'm not gonna do all the work out. That's your opportunity to learn parts that you missed. But I am gonna give you lots of hints and tips, whatever, of how to tackle the problems. And like almost any electrical system that you work on, it's usually really helpful to draw a schematic diagram, right? And so when we talked about doing synchronous machines, we said we need to develop an equivalent circuit of a synchronous machine. An equivalent circuit is something that electrically is equivalent. It's actually not the same, but it's going to give you the correct electrical results. And so if you're going to use electric circuit theory, KVL, KCL, Ohm's law, whatever, to solve these problems, it's really helpful to draw a circuit schematic. I don't know if anybody drew a circuit schematic for problem number one. It's been a while since I graded it, but I don't recall seeing an actual circuit schematic. So first thing I did, I drew one out. And now with that information in the problem, I can populate it and get pretty close to the information I need. The thing is, I still got a couple holes, right? I still need to fill in a few parts. So the first part is, what is VT? Remember, VT is the terminal of the synchronous machine. That's actually what I have the ability to measure, okay? So I can put a multimeter on and I can measure it. So that's going to be a really good reference point because I can check it. So I know right off, I'm going to specify my VT to be an angle of 0 as my reference. The question is, what is the voltage there? Well, it tells you a 4.17 kV Y-connected synchronous generator means that it's rated to deliver 4.17 kV. Y-connected or line to line. In three-phase, we have to do all of our work in single-phase equivalent. So you needed to divide that by the square root of 3. And then you set it at an angle of 0. Okay, that was the first thing, and pretty much the only thing that you needed to do to use some, I don't know if you want to say advanced knowledge, but understanding of single and three-phase to be able to calculate. Now for part one was calculate the current, the load current, or the phase current. Well, load and phase are the same, right? I phase equals I load. Given this information, at this point, you should be able to calculate what the load current is fairly efficiently. So with that being said, how would you do that? How would you calculate the load current? Go ahead, Nazali.
The voltage divided by the combined impedance.
Okay, so one of the classmates has said they took the voltage, the terminal voltage, I'm assuming, and divided it by the impedance, the 0.15 and the J2.2. Is that load current though? Wouldn't that be equivalent to short circuit current? Because the only way you have 0 volts here is what? When you have a short circuit. So if I did KVL, right? EA is equal to I times 0.15 plus J 2.2 plus my terminal voltage, right? You're telling me that this value of I, you'd solve for that by taking this voltage right here and dividing it by that impedance? Probably not, right? That's why it's helpful to draw a circuit diagram, because you can see, oh, wait a minute, the voltage at the terminal is 4.17. So even if I would have divided by 4.17, if I was saying, give me the short circuit current, that actually isn't the correct answer. It should be EA divided by that, right? Because if the terminal voltage is 0, then you can use Ohm's law to solve for that. So that isn't even possible because you have no idea what EA is. So that can't be right. So the I has to come from here. We know that S equals this, right? How many times we put that equation up? Dozens, maybe? Solve for I, plug it in. Well, this is how you solve for I. So this is part A. And then part B is here. I actually intended this problem to be a pretty easy 10 or 20 points was my intention. It didn't work out that way, but that's what I intended. That's it for problem one. The concerning part is that people were not able to get I from that. That's something we've done a lot of, right? So if we're not able to calculate that value of I, we have to go back and review the stuff for chapter one or exam one, because that's when we focused on that, right? That's when we did a lot of problems. But why is this still important? Because in the real world, a lot of times you're going to be given a load at a certain MVA or KVA rating at a certain power factor. You should be able to calculate the current, right? That's the known that you have. The load, the utility tells you the load is 1,000 MVA at a 0.9 lagging power factor. If I give you a nominal voltage of the system, you should be able to pretty accurately calculate what the current is. Okay? That was problem one's question on problem one. No question? All right. Problem number two. Again, draw a picture. I have a synchronous motor, so we know P out is going to be equal to some sort of mechanical power. And it tells you it's 25 horsepower. Right? Remember how we talked about the nameplate rating on a motor would be the actual output power it's capable of providing. The problem is it was given to you in horsepower, but it should be a pretty easy conversion to go from horsepower to watts, right? There's 746 watts per horsepower. So the conversion shouldn't be too bad. Now, the next thing is the input power. Well, I know that I'm dropping off a bunch of powers here. The difficulty is I don't know what those values are. I don't know what rotor copper losses are. I don't know what stator copper losses are. I don't know what friction and windage. I don't have any of that information. But there is something that's really important that I do have, which is efficiency, which is just P out over P in. Can't you calculate P in given the efficiency equation? So this had actually nothing to do with synchronous motor generators. This just had to do with power equations. This is going back to your introduction to circuits, right? When you were taught efficiency. So to solve for problem number one, we didn't even need to know if it was a synchronous. I could have called it a box and said the box has an output equivalent power, 25 horsepower, and the input power is it's 92% or 82% efficient. You're going to be able to calculate that out. The next part is once I had P in, I should be able to build a power triangle, right? What is the angle here for theta? What's the angle for theta? Inverse cosine of the power factor. Very good, Nizali. Right? And I said it was a leading power factor. So in reality, the current leads the voltage. So my S actually has to go down here. Right? The angle should be negative because it's VI conjugate. So this is the one you should have done. You should be able to calculate S with a right triangle, right? If you know the angles. This is all trig. It's maybe high school or pre-calculus, depending on when you took trig. It's just pre-calc. Again, this had nothing to do with any of the material we solved for. It's just, can you use efficiency and power factor effectively? Any questions on number 2? Number 3. You had open and short circuit characteristic data. That should immediately tell you I have to start looking at calculating reactances. And we did a couple homeworks on it. And if you remember, that was our field current plot. This is IA. And this is V. Armature current. And this is V. I should say terminal voltage, not OCC. So here's my open circuit characteristic, right? This is my OCC. My short circuit looks something like this. And then if I have any information, I'm going to try to draw the air gap up to here, right? Because the air gap shows you what the voltage would be if the value is not saturated. And now we can go ahead and start populating data. So at 480 volts, we have a current here of 16 amps. And then on my short circuit data, I see that at 16 amps of field current, I get, let's just call it 452 amps over here. In addition to that, we also had a field current of 21.3, and that gave us a current over here of 601.4 amps. Right? Now remember the deal about X sub S, unsaturated, and X sub S saturated. Unsaturated means you have to use the parameters that the OCC is a linear line. Or the air gap, right? You can use any parameters on the air gap. So you can use the air gap or VOCC on the unsaturated. That's the same thing. And you're going to divide it by your field current at that. For my saturated, it's V open circuit characteristic saturated divided by IA. So now looking at this data, the only thing that I haven't identified is this point right here. This is 14.7 on the air gap line when it reaches 480 volts. Okay. Or if we want to be a little bit better, because it's a Y-connected machine, why don't we just go ahead and put that as a single phase equivalent? So we'll do 480 divided by the square root of 3. And with this information, can you calculate X sub S unsaturated and X sub S saturated? Well, if I wanted to calculate the unsaturated value, I need either the air gap voltage or the unsaturated open circuit characteristic. But then I also need the current at that unsaturated value. Do I know what this current is right here? Do I know what that current is? No, but can I just do the slope of the line to get that? It's a line, it's a straight line, starts at 0. So you can do y equals mx plus b to get the slope of the line to solve for the current at 14.7. Right? Once I have that, now I have the air gap and short circuit characteristic at 14.7. And then over here, I can see that I have that value and that value to calculate the saturated value. So the only thing you needed to do was do a little linear interpolation to get the unsaturated value. And that was it to get the saturated and unsaturated characteristics. And if you remember from the review session before the test, we talked about that a lot. We spent a lot of time going over the curves and the different characteristics, trying to emphasize how you can look at those curves. Okay. So this one was a little bit different because you weren't actually given curves. In some ways, this makes this problem easier because you can actually just use numbers. Instead of having to pick points off the curve, You can actually just look at the numbers and decide from there. Questions on number 3? Any questions? All right, number 4. Do I even need to cover number 4? You should be able to, at this point, pretty easily convert that to radians per second, right? That's just a unit conversion. The second part of the problem is if you connect this machine to a 50 hertz system, what would its speed of operation be? Well, you know, in 60 hertz land, it's 3,600 RPM. So remember, our electrical frequency is equal to 120 times N sub M divided by the number of poles. If you know that that electrical frequency is 60 hertz, you know N sub M, you should be able to calculate the number of poles. Then when you do part B, you rinse and repeat. But now you solve for N sub M because you know what the number of poles are. Okay. That was it for number 4. Questions on number 4? All right. Number 5. So we have a diagram. A prime, B prime. And I said, all right, you've got 2 currents, right? You have IA, the current going into the A winding is 10 sine of omega t plus 180. And IB is equal to 10 sine of omega t. So it says the first thing is determine the next net flux density given the following currents that have been rotated by 90 degrees. Another way to say 90 degrees is omega t equals 90 degrees. So IA is equal to 10 sine of 270. And IB is equal to 10 sine of 90 degrees. It's a sine of 90. One, right? That's equal to 10. What's the sine of 270 or minus 90 degrees? -1. So this is -10. So now the current that goes in the A winding is at the negative peak. So the actual current goes in here. You should be able to use your right-hand rule and end up with a current that goes there. Now I run my current B. Same thing. And so since these are the peak and it says the peak magnetic flux density is 5 times, so BA should be equal to 5 times the peak current. And B sub B is equal to 5, again, times the peak current here. You just have to put the angles together and add them up. All you needed to do. Questions on number 5? Yes, sir.
This is IB equals 10 sine,
Of 90 degrees.
10 sine. Okay.
Yeah, because omega t equals 90, right? So you just add, or you just put omega t equal to 90, and then you add it into those parentheses, and then you just do the signs of those. This one I wasn't sure what to expect because remember when we did the exam review, a lot of people were like, we've never seen this before. I don't know what this is, what's happening here. But then we spent a lot of time during class that day covering that. And that was it for the tests. Any questions? Any thoughts? Comments, conclusions? Yep. Any thoughts? Going once? Yes, sir.
So for question two, part B, I did S over two equal cosine inverse of the power factor.
So you did S over P equals the inverse cosine of the power factor. Is that right? What does SOHCAHTOA say?
So it should be cosine.
What does SOHCAHTOA say? Hey, SOHCAHTOA says the sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, the tangent is the opposite over the adjacent, right? SOHCAHTOA. So if I did my power triangle, and this is the angle that I'm looking for, or maybe I'm not looking for, but that is the angle between S and P. We know this is 90 degrees. This angle, we don't really care too much about. You don't really care about the angle between P and or Q and S. But the definition of power factor is the ratio of real power to total power. If I write that in equation form, it's P over S. So it's not the inverse cosine. It is the cosine of theta, right? That's SOHCAHTOA.
It's still,
SOHCAHTOA?
back at
I'm going to just go with Oscar then. How's that? I'm just going to call it Oscar. I like Oscar better. But I thought everybody said SOHCAHTOA. I don't know. Is it SOHCAHTOA or SOHCAHTOA? No, I know that, but I always thought people said SOHCAHTOA. I don't know. Well, you've heard of Oscar now, so let's just do Oscar. Oscar is not going to have the same problems that SOHCAHTOA or SOHCAHTOA is going to have. So easy to remember, and it's more silly and fun. Any questions on the test? Comments? Okay, well, there were so few, it means you did so well. I wasn't gonna give you a chance to make up points, but seems like you don't really need that, right? Because nobody's having any questions or discussion, so you're all happy with the grade you got and no bonus points are needed, right? There ain't much discussion. Well, that's fine, but it doesn't seem like there's a lot of, oh, how'd we do this? How'd we get that? It seems like everybody's got no questions, and so. Well, I'm saying, don't dream one up.
Well, no, I do have on number one.
Yeah,
So I did, but I tacked on those kind of, data at the end of that.
yep. So you did this, I think, right? And then you did cosine theta. What does that actually equal to? It's equal to P, not S, right?
Yeah.
When you multiply
Oh,
by the
yeah.
cosine of theta, remember the cosine of theta by definition is P over S. So what you did is you did S and you multiplied it by P over S. What are you going to get? P, right? The S's will cancel.
That's right.
We're not asking you questions, we're gonna spend an hour and a half in the office asking you questions.
Oh,
I already know where I would go.
so these guys are saying they should get special. No, I'm kidding, but I'll give you an opportunity for about 15 points. No? Yes? Here's the deal. Redo your test. Get it in by Thursday before class. You get them right, you're clear, easy to follow. You get 15 points on your test. If you don't, there's no punishment. This is only a bonus opportunity. So you're under zero obligation to do this. With that being said, whoever got the highest score, let's say it's 100, which it was, by the way, their score can be 115. How much work do they have to do? Basically zero, right? Just copy their test over again, right? I mean, if they want to make it a little clearer, that's fine. But for those folks who didn't do as well as that, it encourages you to go back, look at what you did, and then maybe do a little bit of additional learning. Remember when I offered this stuff for the first test, it's an opportunity to earn points, not to be given points. And the earning means you're learning. Earn and you learn. Look at that, I'm a poet. As opposed to just being given it, which doesn't necessarily mean you've got any necessarily additional knowledge there. So that's why we're offering that. So again, it's no punishment. It's totally up to you. If you want them, great. If you don't, that's okay too. No judgment here. All right? Yes, sir.
You know, the class average was,
I think it was a 66 or 67. Anything else? TV Land doesn't want this opportunity, right? Because they didn't ask any questions or make any comments.
Kind of saw where I went wrong. So not a lot of questions.
Okay.
TV Land would love this opportunity.
Okay.
Yes. Yes.
I'm teasing. Yes, that would be fair for anybody. But again, this is your opportunity to advocate, talk about what, what could have been different. And also you could say, I just, for some reason, had a bad day, didn't understand something, should have, could have, would have. But there wasn't a lot of new material, right? We just keep building on those same circuit analysis concepts that you learn probably as second-year students, maybe third-year students, et cetera, et cetera. Like I said, that's all I had for, I'm not going to cover any new material because this gives you an opportunity to reflect, go back and think about, what you could have done differently to have more success. That's all I had. Any questions? Nothing? I don't know if I should keep talking because people are just looking down at their work. Does that mean they want to get out or they want to keep working? They want to go back home and digest the material. I mean, that's what you all want to do? Okay. You agree with that, TV Land? Although some of you are already home.
Yeah, I'm already prepping to resubmit for the extra credit. So
Okay. Well, don't do it yet. I haven't made it available yet. So I got to do that. There'll be no place to submit to, but within, I don't know, 20 minutes or something like that, however long it takes me to get back to my office and set it up, it should be available to you. And you can submit it as early as you want. But remember, the opportunity for you is just to give you the chance to learn. So if you need to write more information in there, but that's okay. But be neat, be clear, because if you just rush and scramble, are you necessarily learning? Or are you just copying things over? These are opportunities to get the material in more depth, as opposed to just getting a better grade. So if you just choose to get a better grade, that's fine, but you're not really doing the deep learning that you need or you may need to succeed in the future when you go work in industry. And I've worked on a bunch of projects fairly recently, 1,200 megawatt projects. Offshore wind projects, massive offshore wind projects off the coast of Long Island. Nobody has once said 2,000 amp projects. So all megawatts. So that's what has any value. And if you're doing anything in this industry, you got to be able to understand those concepts. All right. Well, if there's nothing else, have a wonderful day. And I'll see a bunch of you at 2 o'clock, right, for senior project presentations, I think. So, all right. Take care, everyone.